this lecture? And you just say yes or just say I need your consent for the recording of the lecture.
Okay lang, sir.
Okay, thank you. Okay, we'll continue because we have so many things to discuss. Okay, so we will continue our lecture on okay, so we finished. Okay, last time we are introduced to logic gates and the truth tables, and now we will continue on the Boolean algebra. So here's the preview of what we discussed yesterday. So yesterday we discussed how do we perform the following. So we need to put logic symbols, logic truth table, logic function, uh, and we have to create our function formation, function of A, B, C as your input, and this would be your output. Also, your logic waveform that is based on your input and output versus time, and the buffer, inverter, AND gate, NAND gate, OR gate, and NOR gate. Also, we discussed XOR and XNOR. So we also touch up on digital circuit operation. We have the transmitter and the receiver. Also, we discussed the logic levels. And we also define positive logic and negative logic, and also the input DC specification of a digital circuit, which is used also in determining the number of voltage and current. And also uh, we also discuss noise margins, power supplies, and some of the few calculations in your transmitter circuit. And now we go forward also with the switching characteristics. And also we are able to have a short description on datasheets, which is primarily used if you're going to check for the package, the pin configuration of IC, the operating current, and also the collector current of voltage, the limits of operation, as well as uh, the units. Okay, so now we also discussed your module 2. So I add additional information on your module 2 on your classroom. So the deadline would be this Friday or next week. So any questions with your module 2? No. So these are the format if you're going to submit in A4 size bond paper. So you need to save your files in this format. So if I have given you a template, like what I did on the other course, so you need to follow the format. Okay, so we are now going to our main topic for this week. So hopefully we could finish our part two this week on Boolean algebra. So Boolean algebra was presented by George Boole as a yes question. You could resubmit if you want to. Don't worry. Okay, so Boolean algebra was developed by uh, abstract framework by mathematician George Boole. So this framework is essentially launched in the field of computer science. So it was in 1854, and nowadays the implementation of digital logic was based on his work. And after this, it was developed by the American mathematician Claude Shannon, which applies George Boole algebraic framework in his work on switching circuits at Bell Laboratories. And the launching of the field of digital circuit design and information theory was based on Boole's framework. Today, Boolean algebra is often used to describe not only his original work but all of those that contributed to the field after him. So he's one of the famous English mathematician, and in this field, usually we're going to use dot, plus sign, and this symbol. This means earlier when you see this symbol, this means not. So this is a not operation or negation. So this is and 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 this is or. So when you see this dot, this is and this is or, and this is not. So that's the basic uh, operations that we're going to use. So normally in Boolean algebra, there are only two valid states. So it's either true or false. So in this lecture, we're going to discuss the axiom. So when we say axiom is the statement of truth about the system that is accepted by the user. And axioms are very simple statements about the system, but you need to establish before more complicated theorems can be proposed. So axioms are basic, so they don't need to be proved in order to be accepted. So we're going now to discuss the five basic axioms in Boolean algebra. So we have the first one, we have the logical values axiom. So a variable a can only take one of two values, either 0 or 1. If the variable a is not 0, then it must be 1. Conversely, if it is not 1, then it must be 0. So this is axiom number 1. So it provide us the value of your a. If a is 0, if a is not 1, and if a is 1, then a is not 0. So that's the basic Boolean values. Now for axiom 2, so we have what we call the definition of negation. So this axiom defines logical negation. Negation is also called not operation, or the symbol, or what we have is this symbol, or we call it prime. A prime. So if axiom number 2 defines if A is 0, then A prime is 1. Conversely, if A equals 1, then A prime is 0. So that's axiom 2. So for axiom 3, it's the definition of logical product. So when you're using a logical product, the symbol that you're going to use is a dot. And it depends. Sometimes you're going to use ampersand or conjunction symbol. But in this lecture, we're going to use dot. Now for this, we have axiom number 3 is the definition of logical product. A, how do you read this? A and A and B is equals to 1. If A equals B, then it is equals to 1. And if uh, A and B equals 0, it's otherwise. So this is your logical product. Now for the definition of logical sum, so we refer to as the plus sign, or that is your or. So we say now the definition of logical sum axiom is A or B equals 1 if A equals 1 or B equals 1, and A or B equals 0 if otherwise. So this is your logical sum axiom. So the symbol for logical sum is or plus sign. Now we have also the logical precedence, and this defines the order of precedence of the three operators unless the precedence is explicitly stated using parentheses. So example, so not precedes and precedes or. So example, here we have function equals to A prime. This is and B or C. So meaning what you're going to do first. So if you're going to explicitly do this, first you need to have the A prime, then you will have the and B, A prime and B. Then after this, you're going to have or C. So that's what we call precedence. So it doesn't mean that you're going to do the reverse way, because not precedes A and D. So meaning uh, it is always that you will prioritize A and D or and compared to or. So that's why we did not use B or C first, but we use precedence on and for your dot. So now we are done with the action. Now we are going to deal with theorems in Boolean algebra. So what is a theorem? So is theorem is a sophisticated truth about the system. It's not intuitively obvious, but theorems are proposed and then must be proved. So once proved, they can be accepted as a truth about the system going forward. So a person is also a English mathematician. He's a logician also developed during the time of George Boole. It's D. Morgan. So he's best known for his contribution to the field of logic through the creation of these theorems we called as De Morgan laws. So he has established the theorem of duality and the identity. So duality states that an algebraic equality will remain true if all zeros and ones are interchanged and all a and d and or operations are interchanged. So the new expression is called the dual of the original expression. We have the second theorem. It's going to be identity operation is one of when it's performed, a variable will yield itself regardless the variable's value. So after a few slides, we will going to discuss the second theorem of De Morgan. Now, how do we prove duality theorem? So, for example, we have the original expression a and 0 equals 0. So, how do we prove that this equation is 0? So, first we verify the equality. So, by using the proof by exhaustion, meaning it involves plugging in each and very possible value for the variables and evaluating the equality of correctness. So the first value of a can take on is a equals 0 and d with 0 is equals to 0 based on our action for logical product. So as we go back to logical product, so we have if a and b is not equals to 1, then you will have it is equals to 0. So that's based on your logical product. So this becomes 0 and this would be correct. And we have the second value that we can take is that a equals 1. And we refer back that 1 and with 0 is equal to 0 based on our action for logical product. Now, if it is also correct, and we mean that a and 0 is equals 0 is a true statement. So that's for your original expression, but how are we going to do it in a dual theorem? So it's found by interchanging all and or a and d or operations with zeros and ones. So let's see if the equality is correct by exhaustion. So we have this value. So based on our action for logical sum, so we go back to logical sum. So here's the logical sum value. So we have A or B equals 1 if A equals 1 or B equals 1. If they are not equal, so otherwise they are 0. So it's the same way here. Since A and B, so we refer to or. So meaning 0 or 1 is equals to 1. So that is for the logical sum. And based on action for logical sum, it's also correct that A is 1 or B is 1 equals to 1. Through the process of proof by exhaustion, we not only have proved that A or 1 is a true statement, but also a theory of duality held. So this is your duality theorem. is proved by exhaustion. Now we have example. So when we say L, this is low, meaning this is 0, 0, or it is false, false, false. And F is your output, A and B is your input, as we refer on this diagram. So function equals A and B. So in order for us to map, where are we? Okay, so we have to map by positive logic. So we know the positive logic would be what? So this is AND gate. So meaning if both inputs are true, you will have an output true also. So this is your mapping with positive logic. And this is your negative logic. So this is reverse. Now, if we use duality by interchanging and or operations and all one, so what will happen? So this one would be the same way, and this would not be AND gate if we are going to interchange it. So this becomes your OR gate. So after you interchange the values of your input as well as your output. So the truth table is the definition of the logical sum per axioms. So this means that this would create our first function is we have output is equals to your input A or B. This is function output is equals to A and B. So you generated the duality theorem by using the following logic gates. Now we're going to have some of the theorem that is under De Morgan. Now we have identity theorem. So when we say identity, if you're going to have A or 0, so your output is A. And when you have A and 1, you will have A. So that's identity. So in this case, the static input variable can simply be removed from the logic expression, making the entire circuit a simple wire from the remaining input variable to the output. So if you encounter these values, so it means that this is just like your simple addition uh, variable in algebra. Variable a plus 0 is a, and this one is simple multiplication, but we are not saying that a plus 0, that's not applicable in logic circuit, but this would be a or 0, and this is a and 1. So be careful saying this in logic circuit because it would mean different. So always say a or 0. So this is not plus. So we have also properties of null element. So the null element, when we say null, so the values, logic 1 will yield logic 1 regardless of the value of the input variable. So we have this value, and the duality is that adding a variable with logic 0 will yield 0. So we have a or 1 is equals 1. This is a or 1. And this is a and 0. That would generate 0. So this is 1 and this is 0. So null element operation is the one that, when performed on a constant value, will yield the same constant value regardless of the values in the variables within the same operation. Now we have next one is idempotent. So we are having to use an OR value with the results. And what will happen is we have uh, A or A. This is A or A is equals to A. And we have A and A is equals to A. So this theorem holds true for any number of operations, such as if you have long numbers of A. So if you add hundreds of A, it still becomes A. And if you multiply several numbers of A using and, so A and A, A and A, and A and A, so it becomes still A. So that's the theorem of idempotent. Now we have the complement. So complement is famous, is used in the advanced combinational logic mostly. And this would be useful if you know this theorem. You will always need to remember this. So in OR, we say A or A prime is equals 1. So that is the theorem. A or A prime is equals to 1, and A prime equals 0. So this is the theorem of complement. So this describes the operation of variable with the variable's own complement, and this defines the complement of 1 is 0. So that's why you have 0, and you have in OR 1. So it's like saying, if this is 1, if this is not 1, so this becomes 0. So you multiply 1 and 0 is equals to 0. Now, for example, this is 1, and if this is 1, so what will happen is this becomes, since A prime, so this becomes 0. So 1 or 0 is still 1, 1 binary. That is in your complement theorem. Now we go to involution. So we are taking the double complement of a variable which results to the original variable. So we have this gate level depiction of the involution theorem. So we have double negation. So we have A prime prime. So, or we have A2 prime. So it means that you have this is prime, this is prime. So once you double negate, it's go back to its value. So because you this is not A and not A, So meaning it becomes A. So likewise, when we try to demonstrate here, example, this is 0. When it goes on this side, it becomes 1. And if this becomes 1, it is become 0. So meaning 0, A is A, the same still on F. So that's what we mean by involution. So it's just going back to its original input. Now we have another property. We have the commutative. So when you say commutative, we are changing the order of the variables. So when you say A or B equals B or A, so we just change the input order. It's still the same. Now for your duality using A and D, so we have A and B. So I forgot to put here that sign, but usually in other cases, if you don't have to put that sign, it means still and. So you will have the output still the same. For the associative property, we mean associative by grouping of variables. So meaning grouping doesn't change the result of the operation. So you have the original or, and if you're going to have this is a 3 input OR gate to make it more detailed. You're going to have this. This is the associative property. So when we say A or B, this is A or B, and after this, you're going to OR these two values. So you have this circuit for this. Now, it's the same also if you're going to have A on the output and you have B or C on this side. Now, for the duality, so we have this A and B. So this is A and B and C. So, and this is C. So this is your first diagram, and your output diagram is A uh, and of B and C. So this is how it was grouped. So meaning grouping this would not affect your operation, and it would be having the same result. How about this? So this is an example of your functional simplification. Now, if you want to see what is inside the 4 input OR gate, so you will have the following. So F or your output is equals to A or B or C or D. So it means that you have these two as your first two input, and this is your uh, second to the last. So you have C or D, and we have B or A or B, and after this you will have another OR gate. It's going to be still the same. So that's how you simplify. So this is the simplification, but also this is your logic diagram that you created from the 4 input logic gate. Now we have also the one of the famous one. You have the distributive property. So you usually use parentheses operation and to give precedence. So if you have the parentheses, it means you will going to do the operation inside the parentheses. This would give you precedence to the next operation. So example, we have the original. So this one. So we have A and the or B or C. And if you're going to convert this into this, so what will happen? So it's the same saying as A and B, and you have A and C, and the last you're going to do is you have do or. So this is or, this is or gate, this is AND gate, and this is AND gate. So that is the value, and that is the interpretation of the simplification of the logic diagram. For the dual theorem, so you have this equation. So you have A, this is or, and you have B and C. So you have B and C. Now, this dual theorem is also equivalent to this one. So what is the value? So you have A or B, parentheses. So you put parentheses because if you don't put parentheses, the the and sign would try to have different meaning. So this becomes B and A or C would be a different value without the parentheses. So that's why we need to be careful. So A or C, and you have the AND gate. So this is AND gate. So this AND. Okay. So any questions regarding distributive property? So when you see the parentheses, meaning this would be, uh, they will be the first to be used, and the operation outside would be the last. And now we have another example. For this, we have x, y as and you have also this value x and z, but you can able to reduce this into a simplified function. So what will happen is you have, so x would be and you use parentheses, and you have this y or z and x. So that is the simplified form for this given example. Now we have also, after distributive property, we have absorption. What happens in absorption? So the term with logic expression produces the same output as another term. So the second term can be removed without affecting the result. So in this example, we have this one. Take note, if you have only the variable that is the same, but if you have different, this would be a different result. Okay? For this example, this since they have the same values, or you try to short this one, it would be the same. So this becomes which one first? You cannot say that A or A, but first you will have A and B. So this is A and B or A. So the result would be A, since you are referring to what? OR gate, and whatever your output here will be also A, and it would like it's will try to absorb the result here in your A. And now next is you have this one, A and A or B. So this is A or B or gate and A. So meaning you still have A. So this is the absorption property. But we seldom use this sometimes. So this is proving absorption. Why do we have these values? So first we have this, right? So this yield a result of A or B. So this is the original expression. And for the evaluation of term A, so you have this value. This is only for A. And the evaluation of A and B is this one. So combining them, you will have A as a result. So the term A will produce a result of 1 for the input code of A equals 1, B equals 1. So this result is sufficient to cover the result produced by the term A and B for this input code. So when these two terms are ORed together, so it becomes A and B becomes unnecessary because the output is not fully covered by the term A. So we can reduce the expression by simply A. It means that A and B can be absorbed into A. So that is absorption. Now we have uniting. So uniting is that when a variable B and its complement, this is B prime, not B0, appear in multiple product terms with a common variable A. So this is B prime. So example, you have A and B or A and B prime is equals to A. So this is like saying this is not B. And also we have another theorem on A or B, and A or B prime is equals to A. So that is theory of uniting. So this is the proof of uniting theorem. And first, you will try to distribute A, and you let B or B prime is using complement theorem. B or B prime is 1. And you have F equals to 1, and you use identity theorem. A and 1 is A. So this is minimization or combining method that we did on uniting. So now we are on the last topic on function simplification. So it means that the second theorem is simply known as the De Morgan theorem, that is the identity theorem, and so much more. We have techniques that we are going to manipulate logic expression using AND gates and into one that uses OR gates or vice versa. Now you could also use NAND or NOR gates, and it depends on how you're going to use. An OR operation with both inputs are inverted is equivalent to AND operation with the output inverted. So the duality of this is that an AND operation in both inputs are inverted is equivalent to the OR operation. So on the next slide, we have the De Morgan theorem that is widely used in modern logic design because it bridges the gap between the design of logic circuitry using Boolean algebra and the physical implementation of circuitry using the complementary metal oxide semiconductor. So Boolean algebra is defined only in three operations. So we have AND, OR, and the inversion or the NOT. And while CMOS, on the other hand, can only directly implement negative type gates such as NAND, NOR, and NOT. So the De Morgan theorems allows us to design logic circuitry using Boolean algebra and synthesize them into logic diagrams with the basic logic gates and then directly convert them into logic diagrams, which is equivalent to using NAND, NOR, and NOT gates. So this is the function simplification of the Morgan theorem. So the original description is that you have f. This is not a. When you say not or a prime, so a prime or not a, so you have this not or inversion symbol, and also you have b prime, so you have this not gate, and this is your or, so this is your or symbol, and this becomes also nand. So that's this one also can be become as this one, so it's like reverse. So that's why you could use the Morgan theorem to simplify circuitry. Also, in the same way in the NAND gate, so you have a A prime and B prime equals to A prime or B quantity parentheses prime. So it's still the same, but you try to look at it, the inversion bubbles will be on the front. If you use this one and this one, the symbol would be the same. So what else? So we have converting sum of products into one that uses NAND gates. So example, we have this function A and B. So you have A and B, and you have C and D, you have C and D, and F. The last part is you will to use OR. So this is OR symbol, and this implemented also by using this one. So this is just putting inversion, but once you inverse this using the theorem of we go back, it's going to be the same. This one, involution. So using the theorem of involution, so the output will be still just a normal line. It's the same. It's like you just write this and you go back again. So it means it's one line, the same. And with this theorem, this would be equal to this value. And now, what is the difference is that if we use a different symbol, this is NAND, this is NAND, and what will happen is you will have this value as your uh, NAND gate. Give me a sec. Okay, sorry for the visitor. Okay, so we have the sum of the products. You could implement it in either and or. So whether you choose and or, as long as you have a different or meaning, so it depends on how you implement these values. So this one would be the same meaning as the last one. Also, this one is the same as this one. It's double bubble. So this one, if you use this, if you move the bubble, so you will have this one will be based on the previous this result. As you remember, this is and. So that is application of your De Morgan theorem. So this symbol becomes this symbol. And also we have some of the function simplification. So this is a traditional method. So f equals a prime or b prime. This is the original. Then if you put two bars, so what will happen? You have involution, so double negation, but the result would be the same. And after this, you have an inversion that can be broken into parts. So it means that you could have the expression also involution to remove the double negation. So these two now will be removed because of involution, and you will have your final expression as this one. This technique is the Morgan theorem that the OR gate with its input is inverted is equivalent to an AND gate. So we have this final answer. So if your answer is this one is correct, if your answer is this one is still also correct, and they will have the same result. So this is another De Morgan theorem. So we have also the NAND function simplification, and we have if you have input to use this input tied together, it means that you have only either 1 or 0. So in cases you have this example, the symbol is like your inverter. So if you have this symbol, it's equal to this one. Also, if you have a NOR gate that is tied together, so you'll have still an inverter. So means your A and B are the same, but when your input is 1, your output will be 0. So it's the same also. So that's NOR simplification. But in the summary, so these are the properties that you need to consider in solving function simplification. Example, I'm going to give you a circuit. You create your function by applying this. So don't worry, you have enough time to open the notes on this because I know this has too much information and too much theorem to deal with. And I think we are on to the last slides already. For the summary, Boolean algebra defines the axioms and theorems that guide the operation that can be performed on two-valued number system, and it allows logic expression to be manipulated to make circuit synthesis simpler, and they also allow logic expression to be minimized. And Boolean algebra produces logic expression in two common forms. These are sum of products and products of sums, and the combination of involution and the Morgan theorem. So this can also converted into a equivalent logic circuit that can use only NAND or NOR gates. Taking the dual of the positive logic function produces equivalent function with negative logic if the original order of precedence is maintained. You use precedence by using parentheses. Identity theorem is useful in reducing circuitry. Also, null element theorem is also useful in reducing circuitry, and the particular input will never change values. In idempotent operation is one of that has no effect to the input regardless of the number of times the operation is applied. Example, you have number of A, uh, 1 million of A is still A. 1 million of B is still B if you add or if you use or and. Also, involution describes the results of double negation. Distributive property is used as logic manipulation technique. So it can be used to make direct circuit synthesis to reduce the number of logic gates necessary. Absorption theorem is better understood by looking at the evaluation of each term with respect to its original expression, especially if it has the same variable. The uniting theorem, also called combining or minimization, provides a way to remove variables from an expression when they have no impact on the outcome. This theorem is one of the most widely used techniques for the reduction of number of gates needed to in your next topic on combinational circuit. So that's why we have to reduce the number of circuitry. So that's the use of the Morgan theorem. And I think we are finished. And these are the references for your lecture. And I'll give you the copy of this in your, I'll give you the copy in your Google Classroom. Any more questions regarding our lecture 2? And we are done. Are you still there?
Yes, sir.
Okay. So I will end the recording.